Hello, thank you for coming to our talk. My name is Chris Cummings, and with me is Sean Cummings. We're not related, who is the student assistant for this project that we'll be talking about today. So yeah, thanks for coming to this talk. The talk title is DPDK as an offload engine for P4 SmartNIC applications. So we're going to be talking a little bit about how this summer we, mostly Sean, built a P4-based, an FPGA P4-based SIIT-DC IPv6 IPv4 translator, and how we use DPDK to offload the more complex functions that we didn't, want to do in P4 or couldn't do in P4 out of the FPGA. So yeah, I'm Chris Cummings. My role is network automation software engineer at ESnet, the Energy Sciences Network. I'll go into who we are at ESnet a little bit in a second. Sean, do you want to introduce yourself as well?
Yeah, I'll just give a quick introduction. My name is Sean Cummings. I go to Illinois Institute of Technology in Chicago. I'm a fourth year. Um, I do networking research there, and I've been working with Chris this summer on this project. So
Cool. All right. And thank you for having us at this conference. It's an exciting opportunity to present. So first things first, I'll just go and give a little bit of background about what ESnet is and why we would want to build something crazy like this. So ESnet is part of the Department of Energy. We're a Department of Energy user facility. And basically our role is to connect all of the high energy particle physics institutions that are DOE funded to other high energy particle physics research institutions, as well as other DOE science concerns. So essentially we run a really big internet provider style ish network that allows science data to flow. And we'll talk a little bit about why science data on a network of this size has some unique traffic implications around how that traffic is used. So as you can see, the network is national to the US mostly, but we do have international connectivity to Europe and specifically for the CERN project, as well as other high energy particle physics projects there. So we have our own fiber network and our own routers and basically everything you would have in a traditional service provider style network. But we are not quite a traditional service provider network. So we are an R&E network, or a research and education network. So in this diagram here, you can see that there are, ISPs. So that think, your Comcast, AT&T, the big providers who maybe are tier ones and don't peer with anybody or peer with everybody, but don't, buy transit from anyone. They connect to content service providers like Google, maybe businesses like, a car company or an insurance company. There's a lot of those style networks. Then there's R&E networks, which there's also a lot of. So there's some like ESnet, which connects the DOE big science facilities, Internet 2, which provides in the US science network connectivity for state networks, regional science networks, things of that sort. And then these regional networks over here are connecting libraries, universities in a geographical area. There's also European NRINs. There's a ton of those that are very similar to the ones talked about here at the US. Géant's another good example of this, very similar to Internet 2 and ESnet style research and education networks. So we're part of the internet, and we're part of the internet early on. However, we are kind of different because we're working in this research and education space. So one way in which we're different is that a normal ISP is going to be more like this freeway interchange where you have a lot of different paths to a lot of different places, and you have relatively small traffic that in aggregate adds up to a lot. But these smaller flows are different than what we see on a science network. So on a science network like ESnet, we might have more purpose-built dedicated flows. So these really big elephant flows versus mice flows, right? These big elephant flows, kind of like a bullet train here, that are moving vast amounts of data from point A to point B, and the network's not in use for as much general purpose traffic. And so that has kind of some unique constraints and requirements that trickle down to running a network like ours. So let's talk a little bit now less about what ESnet is and more about this SIIT-DC DPDK P4 FPGA buzzword project that we built. So the project background has something to do with how there's this little protocol called IPv6. Probably heard of it. It's pretty important, and it is the future of networking. And the future is here, but it's not all the way here. So because the future is not all the way here, We have to kind of figure out ways to exist in this in-between time. So some things can't be upgraded yet for IPv6. A good example of this is, scientific instruments. They're purpose-built on big, decades-long projects, and if they're older, they may not support IPv6, and they may not be able to be upgraded to support IPv6 without spending tons of money to replace the entire instrument in ways that are just not feasible. However, there is a OMB mandate around IPv6 that now means we have to be moving towards IPv6 only networks. So we can't even, in the US federal government space, necessarily dual stack as much anymore, and we have to move to single stacking IPv6, which is great, but we still have to allow these v4 only segments of the network and these v6 only segments of the network to communicate. So how do we do that? Well, there's a tried and true solution that has been used throughout all the time of network engineering as long as it's existed, which is NAT. So that's where this project comes in, and building a SIIT-DC translator that can handle more abnormal traffic flows than what you would see in a commercially available product. A lot of commercially available products that can do NAT are working more under this idea of small flows in aggregate versus what we've built is geared towards translating small flows that are really big. And that's where the FPGA side really comes in to benefit here. So we settled on a technology called SIIT-DC, stateless ICMP and IP translation data center. So it's an architecture defined in RFC 7755. Sean, correct me if I'm wrong on that one. But basically, it outlines in this RFC how you can use an assembly of various translation technologies to basically run a IPv6 only data center with IPv4 only segments of your network and allow those single stack segments of your network to communicate to each other. So in this diagram, we have an example, which we're kind of going to be using as we talk through what we've built. So the big thing here is the SIIT-DC border relay. So that's what Sean has been spending the summer building using our tech stack, which is the ESnet SmartNIC tech stack, which he'll go into a bit. But this border relay essentially sits between an IPv4 only network and an IPv6 only data center. Also on this diagram, you can see that there's an IPv6 only network with IPv6 only clients. And then there's, of course, the IPv6 only servers. So this would kind of show maybe you'd have, using the example from before, a scientific instrument over here where the IPv4 only client is that needs to transfer data to some of these IPv6 only servers. So let's actually walk through some of the details here. So inside of the border relay, we actually have some mappings. So we map an IPv4 subnet, and it can just be a single prefix like a /32 in v4, a /128 in v6, or we can just do an entire subnet one-to-one map if they're the same number of bits available. So here we have a /24 and a /120. So you can imagine, address 192.0.2.1 maps to 2001 DB8::1. So here, and I'll show this in a slide, if the IPv4 only client wants to connect to the IPv6 only server, it's going to use the assigned IP out of this explicit address mapping table. And then we also have the XLAT prefix, which is used to stuff the entire IPv4 internet into a v6 prefix. And that IPv4 internet would be, in this example, the IPv4 only client shown at the bottom here. So using the v4 in v6 notation, you can see what a packet from the v4 only client to the IPv6 only server would look like. So if this was a TCP SYN, for example, the source IP would be 198.168.100.1 from the client, destined using your normal DNS lookup methods of, just an A record. You'd probably use split view DNS in this scenario. Destination IP of 192.0.2.1, which is basically through the IPv4 only network announced as a prefix that the network just knows how to get to basically this entire /24. And that packet is going to leave this IPv4 only client, go through the network, end up at the border relay via normal IP routing and Ethernet forwarding mechanisms. And the relay is going to receive that. It's going to look that up in the explicit address mapping table, and it's going to perform the translation on the IP header. So this is just a basic, again, TCP UDP style packet. So here you can see we stuff that source address, the source IP, into the XLAT prefix, and then we rewrite the destination IP to the v6 explicitly mapped address. So then let's say we get a SINAC back from the server. The IPs are obviously swapped from what they were before because the server's replying. The server replies to that IPv4 and IPv6 address, which again is just normal IPv6 address, but we just, if you're not familiar with this format, you can represent it with mixed decimal and hex, which is kind of nice and handy to see. Later on, we'll actually be referring to it in hexadecimal. But the XLAT prefix is also announced into the IPv6 only network so that the server's response knows its way through the network to get to the border relay. Then the border relay knows how to translate that back to the source IP and the destination IP that we would expect on the v4 only network. And the nice thing about this technology that I haven't mentioned yet is that it's stateless. And the stateless portion is really important. And Sean will go into the details of why that's important from an implementation standpoint, but it's also important from a scalability standpoint. So if you want to scale this out, you can just add more of these relays in parallel and you can scale it really wide. So there's an example experiment that has a bunch of 25 gigabit per second FPGA data acquisition cards that are just sending data at full speed, 25 gigs all the time when the experiment's running. So using this methodology, you could have this approach scale out horizontally to as many data acquisition sensors as you have and send that across your network. So it's really nice from a stateless standpoint to be able to do that without having to do any complex state tracking and just rely on the protocol's stateless nature. So enough about me talking. I want to hand it over to Sean, who is really the brains behind this whole thing and has done all of the really hard work of building this. And Sean's going to talk us through the architecture of what we built here. Sean, take it away.
All right, thanks, Chris. So as you can see here, we've got like the two portions of the application that are important. There's the P4 program, which is sitting on the actual FPGA, and there's also DPDK, which is sitting on the host. So the way that this is going to work is that for most traffic, like TCP UDP flows, the traffic is going to go in on CMAC, or is going to go into the P4 program, and it's just going to go out the opposite port. So if it goes in CMAC 0, it's just going to go in CMAC 1 if it's processed normally. But for some edge cases, like for more complex packets, we're actually punting them to DPDK. So that occurs via sending them on PF0, which is actually it's not a physical port. This goes to the host via PCIe. So Chris was talking a little bit about why it's important that our application was stateless, and this will actually explain a little bit of why we architected it like this. So the way the ESnet SmartNIC framework, the state of it when we started was that it's pretty hard to include state within your P4 programs. There are ways to do it, and it's actually evolving. So now they do have examples of like using using externs and stuff, and you could use an extern register now. But the reason we did that is because that's why the protocol being stateless is important here. So I'm going to go on to the oops. So talking a little bit about the hardware that we use. We use the Xilinx U280 FPGA. Got two 100 gigabit ports on it. Then it's got the 8X PCIe Gen 4. So that's the PCIe that we're sending over for sending packets from DPDK, or sending packets from the FPGA to the host. Another thing is corresponding with this Xilinx FPGA here, the specific flavor of P4 that we're using via the ESnet SmartNIC framework is VitusNet P4. So we use that, and I'll show a little bit about the ESnet SmartNIC hardware block diagram. So real quick, I'll just explain the ESnet SmartNIC hardware block diagram. this whole framework is just a framework for developing applications on the FPGA. So there are lots of different components. There's lots of different repos, but the purpose of them is all to develop and deploy applications. So it includes all the tools from like simulating just the behavior of the P4 to simulating like RTL to eventually like building and deploying your application. So now I'll show kind of, or I'll explain a little bit what some of these things mean again. So the PF0 at the top is what I was talking about, PF0, PF1, those are the physical functions. So remember, those are connected to the host via PCIe. So this is virtual on the FPGA, sending it to the host via PCIe. Then there's also CMAC 0 and CMAC 1. So these are the physical ports, the 100 gigabit Ethernet ports on the FPGA. So just the general flow of a packet when it comes in, it's going to come in on either CMAC 0 or CMAC 1, and it's going to go to the ingress switch, which will then send it down to the SmartNIC app. So that's where our P4 program actually lives in this thing logically. So after the P4 app is done, it will either send it to drop if the packet didn't work for some reason, or it's going to send it to the egress switch, where it will be sent out to the corresponding host. Oops. So now we'll talk a little bit about the fast path again. So with this, we decided to separate certain packets. Not all of the packets are going to be treated the same by our translator. Like, for example, TCP UDP packets are going to just go directly into the P4 app, and they're going to go in one port and out the other after being forwarded. So the P4 application will do the translation. It'll translate the relevant fields in the packet, and after that, it will forward, because this RFC. It's actually a router as well. It's just a pure translator, so it's gonna take in the packets, and based on the table, it will forward them to their next destination, and it will go, and after that, it'll be just sent out. So I'll go a little bit later into why we built it out like that, why we chose to do DPDK. It will become more clear once I actually show the packet diagrams. So here's the fast path on the ESnet SmartNIC hardware block diagram. So you can see it comes in on CMAC 0, that's the physical port on the FPGA, it goes to the switch, goes to the SmartNIC app, and then it goes out CMAC 1. So that's going to go from V4 to the IPv6 connected network, which is connected to the FPGA via CMAC 1. So I'll show an example of how this would work. This is an IPv6 packet. So this would actually be, if this were to come in on the block diagram, this would come in on CMAC 1 and go out CMAC 0. So you can see the untranslated source address is within the, you can see that the source address and the destination address are there. So based on the explicit address mapping table, we're actually going to translate those addresses, which will then be like, the packet would then be forwarded based on those, the translate address, which will result in the Ethernet header being updated as well as the other headers. And another thing, when going from IPv6 to IPv4, IPv6 doesn't have a checksum. So we have to add that checksum on in. That's something that we have to do. It's not a functionality that we have available to us easily just out of the box in VitusNet P4. So that's something else we had to build out in software in P4. So you can see that the addresses are translated here based on the explicit address mapping table that was in the earlier slides that Chris showed. And after that, the packet has been forwarded to its proper destination. So this will end up going out CMAC 0. And now just showing the same thing with a UDP packet, except this is IPv4, IPv6. So here we just do the IPv4 has a checksum, but IPv6 doesn't, so we don't need to worry about that. We just have to update the source addresses forward, and then we go down to UDP and update the checksums there as well. So this is what the translation is going to look like. You can see the checksum has been updated. So now we're going to talk a little bit about the slow path. So for the motivation behind this, there are just some of these packets are not very easy to process in P4. P4 is really good at packet processing, but it's best with like fixed length packet processing. Another thing about P4 is that it can't do any recursion, so I can't just say, okay, I'm going to call the translation function on this inner IP packet because the inner IP header, because as you can see here, this ICMP4 header has a inner IPv4 header within it. So I can't just say, okay, I'm gonna translate that inner header and egress it out. It doesn't work like that. So that's one of the reasons. So we built in DPDK. There's actually an offload function. So when we receive packets like this, the P4 program will find that it'll say, oh, okay, this is a TTL exceeded packet, ICMP error packet, and it will send it off to the host via PCIe. So this is another thing that ICMP6 error has the variable length body. These are pretty difficult to chase down in P4, the size of these. So it's better to just forward them off to DPDK where we can do more complex processing in software. So I'll show the whole slow path thing again. So the packet is going to come in on CMAX 0 and it'll go to the P4 application. P4 application will then say, oh, I can't handle this packet, and it'll punt it off to the host. So the host will send it in on PF0. So once that happens, DPDK will process the packet, it will do the translation, translate the inner headers, all of that, and then it will go back out PF1 and CMAC1. More specifically, just to give a little bit more elaboration on what P4 is doing. P4 actually does do the translation either way on the outer IP header, and it will also do, in the case of IPv4, generating the checksum. But the reason we did that is for reducing the amount of redundancy we have to have with having multiple sets of tables between P4 and DPDK. So that really reduces the complexity there if the forwarding tables are just only in P4. But that way P4 only does the packets that it's really good at processing, and it does the same operations over and over again. So now I'll show this on the hardware block diagram. So it's going to come in on CMAX 0 again. It goes down to the app. The app does the little forwarding, and it says, okay, this is not a packet I can process. It'll send it off to a host. Should be host 0, but it's and then after it will come back in on host 1, which will cause it to go out CMAC 1. Okay. So here's an example of a translated ICMP or untranslated ICMP packet. So you can see you got the notable things. You got the embedded IP header that we kind of have the bottom arrow pointing to. The address will be translated as well, but look at the bottom IP header. This is going into a little more incremental detail on it. So within this IP packet, there's an inner IP header. So we have to actually translate that as well. But notably, we aren't doing a forwarding based on that inner packet. We're not translating the address and then doing a lookup in a table based on it. We're just translating the fields from IP4 to IP6. And here's the same thing with ICMP6. Translated ICMP6 error. It goes, we have the inner IP6 header. So going from IP6 to IP4, we generate the checksum, and then we also translate that inner header. So this is pretty reasonable to do in software with ICMP6 specifically, but with With just P4, it's pretty difficult to do just because of the length of the header is pretty difficult to chase down. So yeah, that's pretty much the implementation stuff. So now I'm just going to go over kind of the takeaways from this. So P4 is limited by design. It's supposed to go really fast and it's supposed to not have loops. You're not supposed to, yeah, you're not, they don't want packets getting sent back and forth into the network over and over again. Um, they we don't want some kind of runtime errors with P4. So there's things like there's no loops or recursion, there's no variable length packet processing, or there is, but it's complex. There's if you want to do complex specific functionality, like for example maintaining state, you're going to want to use externs. And yeah, there's limited support for maintaining state. So the nice thing about this setup that we have here is it really allows us to get the best of both worlds with using P4 and DPDK because we get the high performance of an FPGA, 100 gigabit per second. So we get that while also being able to just offload some of the more complex packet processing. We also get some of the more benefits that are associated with that. So, and not to say that DPDK isn't performant, but uh, it's not going to be 100 gigabit single flow. So now I'll talk about a little bit about some of the possibilities that this opens up. So you could perform, as we did here, more complex packet processing operations. So if you want to do anything that requires like you to recurse or anything like that, the world is your oyster. You can do that. Another thing is some of these ideas are going to be, more and more out there. Prototyping externs without Verilog VHDL, I think that's a big one. There's a really complicated debug process with sticking these things all together with Verilog and VHDL and C, and also requires kind of a guy, if you're just one person, a guy that can do all of this stuff, you know, that's so it's a lot easier to just be able to write the externs in software because writing software is a lot simpler. Another thing is you can develop stateful applications with this. So using this same kind of setup, like you can exchange state between P4 and DPDK. So if you are writing an application and you don't, but as long as you don't necessarily care about a little bit of a delay, because obviously it's not going to be as fast. But if you for whatever reason, if you're exchanging some state and you don't care as much about the speed, you can do that with this setup. Another thing you can do is you can make quick table updates at runtime. So the ESnet SmartNIC framework supports doing some gRPC calls in order to update tables. You can also do it with this. Requires a bit more work, but if you needed to optimize the speed, you could directly write into the table memory of the tables. So just the challenges that we encountered along the way, dealing with some of these bit offsets is difficult. It takes a while to build this application actually on hardware. Flashing the FPGA, it takes a while. So yeah, but the nice thing is the ESnet SmartNIC framework does provide a lot of tools to make this simpler, like the RTL simulation. If it works in the RTL simulation, it should. I mean, that's how it was for me. It should work in hardware. So that is nice that we had those tools where you don't have to wait, 6 hours between testing your application. So with DPDK on the DPDK side, the packet processing framework is definitely not as user-friendly as P4. It's not made for that necessarily. It's a little bit harder to use. It's pretty verbose. What we did was we used a ring buffer to process the packets. So you have to kind of manage that as well, which is not something you have to care about in P4 because in P4 the idea is like the abstraction is one packet at a time. But in DPDK you get like a huge burst of packets and you process those. So you have the ring buffer to make sure we don't do any or to make sure that we have, the packets are processed individually. So DPDK also has like less syntactic sugar when compared with P4. So there's a lot less, it makes things a little bit harder to do. It's also a little bit harder to directly manipulate bits within C as compared to P4, because P4 is made for that. So that's the end of our presentation. Thank you to everyone who helped along the way. Also, thank you guys so much for listening to us. I really appreciate it. It was really fun presenting here.